here, and today I will talk about some class of crystals which are coming from the representations of the quantum group for the general linear Lie algebra of infinite rank. And especially I want to talk about the extremal weight crystals. And actually the notion of extremal weight crystals is which was introduced by Kashiwara is a generalization of both highest weight crystals and lowest weight crystals. And I want to talk about the combinatorial realization of the extremal weight crystal for this Lie algebra, and also their tensor product rules. And we also know that the highest weight representation of general linear Lie algebra is very closely related to the theory of symmetric functions, because the character is just, the symmetric function is just the character of the highest weight representation. So the result in this talk can be viewed as a natural extension of the classical well-known connection between symmetric functions and the representations of general linear Lie algebra. So let me start with some of my motivation and some brief background. So let G be a symmetrizable Casimir algebra, which is a generalization of a simple finite dimensional complex Lie algebra, and usually infinite dimensional Lie algebra. And let UQ of G be the quantum group of our Casimir algebra G, and it is Q. It is usually considered as a Q analog of the universal enveloping algebra of G, which was introduced by Drinfeld and Jimbo. And also, since the birth of the quantum group, the representations of the quantum group has been studied by many people. And also, in the early 90s, Kashiwara introduced a very nice combinatorial object called crystal base, which are associated with the highest weight representation of the quantum group. And a few years later, he introduced a new class of crystals. So, for which one? Okay. So, let us consider an integral weight, not necessarily dominant or anti-dominant. And Kashiwara showed that there exists an integrable UQG module B of lambda, and also he showed that this has a crystal base, say B of lambda, and also it has a canonical basis too. And the crystal B of lambda does not depend on its integral weight, but on the Y group of the given integral weight. So if W is a Y group of Casimir algebra G, then B of lambda is isomorphic to B of W lambda. And moreover, if the integral weight is dominant, then this crystal B of lambda is isomorphic to a highest weight crystal. And if lambda is anti-dominant, then B of lambda is isomorphic to a lowest weight crystal. So this class of crystal can be viewed as a generalization, including both highest weight crystal and lowest weight crystals. And let us simply call this crystal an extremal weight crystal. And for example, if G is of finite type, then every integral weight is phi group conjugate to a dominant integral weight. So extremal weight crystal is nothing but highest weight crystal or lowest weight crystals. But if G is of affine or the other cases, then there is the extremal weight crystals are strictly larger than the class of highest weight and lowest weight crystals. And as in the case of highest weight crystals, it is a natural question arises whether we have a nice combinatorial realization of extremal weight crystals. So there have been several works for affine Casimir algebras. The first one was given by Naito and Sagaki. And they gave a Lakshmi-based Chaudhary path model for level 0 extremal weight crystals for affine Casimir algebra G of finite rank. And also, Hernandez and Nakajima gave a monomial realization for also level 0 extremal weight crystal for affine Casimir algebra G. For affine Casimir algebra G, if the level is non-zero, then the extremal weight crystal is isomorphic to highest weight crystal or lowest weight crystal. So interesting thing happens when it comes to the level 0 extremal weight crystals. And actually they play a very important role when you understand the level 0 part of the Lucid's modified quantum group. And so my question is, and my goal is that whether we still have a nice combinatorial description of extremal weight crystals if G is of affine type with infinite rank. Because the reason why I'm interested in this case is that if we consider infinite rank cases, then this case is more closely related with the theory of symmetric functions or theory of Young tableau or semi-standard tableau. So for this, before going to our object, let us briefly recall the notion of crystals. And so we say that a set B is abstract or just G crystal if it has the following daters. The first one is a weight function from B to the weight lattice P, and the functions epsilon and phi, which are parameterized by the simple roots of our the algebra G from B to the non-negative integer with some formal symbol minus infinity. And finally, some operators from B to itself with formal zero notation, also parameterized by simple roots, satisfying the following conditions. The first one is that the difference of these two phi values and epsilon values is equal to the pairing of weight of B and the covers, simple covers alpha check. And the next one is that if E alpha B is not zero, then the epsilon value of E alpha B is decreased by 1, and phi values is decreased by 1 and increased by 1. And the weight of E alpha B is the sum of weight of B and alpha. And we have also similar condition for the F alpha operators, plus 1, minus 1, and minus alpha. And finally, the most important condition is that if we obtain B prime element, if we obtain an element B prime from B by applying the operator F alpha, then it is actually if and only if we can obtain B from B prime by applying the E operators, to B prime. And usually these operators are also called the root operators or Kashmir operators. And from this definition, we can see that the crystal B can be viewed as a colored-oriented graph. This means that actually from these relations, we can draw an arrow from B to B prime, and the arrow is colored by the simple root alpha here. So the vertices are the set B, and the arrows are colored by the simple roots of the given Casimir algebra G. So next, let me talk about tensor product of crystals. So as in the case of usual representations of Lie algebras over quantum groups, we can take a tensor product of two representations. We can take the tensor product of two crystals to obtain a new crystal. So if I have a two crystal B1 and B2, so let B1 tensor B2 be as a set, just the Cartesian product of these two sets. But we still use the tensor notations. And we define the weight of a tensor element to be the sum of these two, sum of the weights of these two elements. And next, we define Cauchy operator E alpha by applying E alpha to one of these the elements in the tensor product, depending on its phi value and epsilon values. And also similar formulas for the F alpha operators here. And we define the epsilon and phi values of these tensor elements by some technical formulas. Then we can check that this set with these data form also 3 crystals. So now let me talk about the Lie algebra, which I'm interested in today. So let GL positive to be as a vector space to be the span of the elementary matrices whose column and row and column indices are parameterized by positive integers. And also we can actually form the Lie algebra with respect to the user commutator. And we call this Lie algebra the type of A plus infinity. And the weight lattice for this Lie algebra is the free abelian group generated by epsilon weights epsilon I. This is just the dual basis of the diagonal elementary matrices with respect to the canonical pairing. And the simple roots of this Lie algebra is alpha I parameterized by positive integers, and alpha I is just the difference of epsilon two adjacent epsilon weights. And the thinking diagram of this Lie algebra is of the following form. It is just the one-side infinity of the finite rank type A. And it is well known that if we put P plus to be the set of dominant integral weights, then the P plus is naturally in one-to-one correspondence with the set of partitions. Here, if we have a partition lambda, then the corresponding dominant weight omega lambda is given by the linear combination of this form, where each part of lambda A is the coefficient of these weights. So now let us consider the examples of crystals. So the typical one, highest weight crystals. So let lambda be a partition and denoted by B of omega lambda, the crystal of the irreducible highest weight module with the highest weight omega lambda. Then the existence of crystal base was proved by Kashiwara, but how to realize it is another problem. So we have to solve it in each type of Lie algebra or Casimir algebra. But in this case, it was proved by Kashiwara and Nakashima that the B of omega lambda can be identified with the semi-standard tableau of shape lambda, where here, for example, if we have a partition 5411, then we feel most of the audience are familiar with this object. But anyway, we fill this Ferris diagram with the positive integers, and entries are weakly increasing and strictly increasing along the columns. And then what is the crystal structure of this Young tableau? So first, we have to realize that the set of positive integers can be viewed as a crystal of the natural representations, so with the highest weight omega 1. And the crystal graph is given as follows. Here, the vertices are positive integers, and here there are colored arrows. So the one arrow means that if we apply the F operator corresponding to the simple root alpha 1, then we get 2. And applying F2, we get 3, and so on. Then, next, we read the words of the given Young tableau by column from right to left, and in each column we read the entries from top to bottom. Then we get a word from a given tableau. So we have a natural embedding of the set of semi-standard tableau into the set of words with the entries from natural numbers, and the length of the word is just the sum of the given partition lambda. Then from the tensor product rule of crystals, we can apply Kashmir operators to the set of semi-standard tableau, and then we can prove that actually this set is invariant on the Kashmir operators, so it forms a crystal. And also it can be proved that it is isomorphic to the crystal of the highest weight module. So next, let me talk about lowest weight crystals. So given a partition lambda, so we let B of omega lambda minus omega lambda to be the crystal irreducible lowest weight module, and this is just a dual crystal of the highest weight crystal, which means that dual means that so from a given crystal, the dual means that we still use the same vertices, but we use the Chuck notation on each vertices, and then we reverse all the arrows. And also, for each vertex, the weight of the vertex in dual graph is obtained by multiplying just by -1. But still, here we model, just a slight modification. But so actually, B of omega lambda minus omega lambda can be identified with the semi-standard tableau. But here we use the entries in uncheck. Here is just a set of positive integer with check notation, and linear ordering here is the reverse one of the usual linear ordering. And the shape lambda check here means that it is a skew diagram which can be obtained from lambda by rotating by 180 degrees. So it is a semi-standard tableau of a skew shape. For example, for the partition 4 to 2, we have a Young tableau of this form. Here, the linear ordering is reversed, so here the entries are increasing, actually increasing and weakly increasing and straightly increasing. And the crystal structure is the same as, almost the same as we have defined in case of high-weight crystals. So the uncheck can be viewed as a crystal graph of the dual crystal of the natural representation. So the crystal graph here are reversed, and the weights are the minus ones. And we read the entries here, and we get a word, and we can embed this set into the set of words and apply the Kashmir operators, and then we can check that actually this set is invariant on Kashmir operators. So it forms a crystal, and isomorphic to the lowest weight crystal. Okay, so let me move on to extremal weight crystals. So let us remark some basic properties of extremal weight crystal for our Lie algebra GL positive. So if lambda is integral weight, then first we can prove that the crystal, oh, I forgot to mention that both highest weight crystal and lowest weight crystals actually connected one. And in case of highest weight one, there is a top element whose entries are, actually the top one is the semi-standard tableau where the first row is filled with 1 and second row is filled with 2 and so on. And the other semi-standard tableau actually can be obtained from the top element by applying finite number of times the Kashmir operators F alphas. So it is connected one. And similarly, the lowest weight one is also connected, but we have a minimal element. And the other semi-standard tableau can be applied by finite number of times the applying the operators, E alpha operators. And still, in case of extremal weight crystals, we can prove that it is connected, but there is no highest weight element nor lowest weight element. And from this connectedness, we can check that the crystal B of lambda is isomorphic to the connected component, some connected component in the tensor product of highest weight crystal and lowest weight crystals. Here lambda prime and lambda 2 prime are dominant integral weights whose difference is the given given integral weight lambda. And actually if we consider the highest weight element u lambda prime and the lowest weight element u minus lambda 2 prime, and then we consider the connected component as a graph, then it is isomorphic to the extremal weight crystal corresponding to this integral weight. And also I'd like to remark that actually the extremal weight crystal depends only on the Y group orbit of the given integral weight, and actually the set of the Y group orbits in the weight lattice is naturally in correspondence with the set of pair of two partitions, so Sigari partitions. For example, if we consider the orbit, the W orbit of this integral weight, this is a sequence, but we can view it as a linear combination of the epsilon weights. So this is just nothing but the sequence of the coefficients appearing in the integral weight. And the Y group here is the place permutation here. So in this orbit, we can take this integral weight, so moving the positive entries to the one side and the negative ones to the other side. Then we can pick up two partitions, 5, 4, 4, 1, and ignoring minus sign, we obtain another partition, 3, 2. So from now on, let me denote the crystal B of lambda by just B sub mu and u. Here, this bipartition corresponds to the Y group orbit of this integral weight. And also, we would like to remark that when the second partition mu is empty, then B sub mu empty is nothing but highest weight crystal. And if the first component is an empty partition, then it is the lowest weight crystal. So let me talk about the realization of this extremal weight crystal. So for a given two partition mu and nu, let me define another B sub mu and nu to be the set of certain bi-tableau S and T, which is satisfying certain conditions. So first, the first one is the Young tableau, usual Young tableau with the shape mu, and T is the dual Young tableau coming from the partition U. And there is one more technical condition. So it's rather complicated, but let me explain it. So here, so there are some conditions on the first column in S and T. So here, S to the I comma 1 is I1 is nothing but the entry in the first column of S, and also lies in the ith row. And T sub I1 is also the first column from the rightmost column here, and also lies in the ith row. And we require that for each positive integer k, that the entries here less than or equal to k, and the number of entries in T which are greater than or equal to k check, the sum of these entries are less than or equal to k. So for example, here, for a given partition, these two partitions, let us consider this element. So if we take k, so for example, let's take k to be 3. Then here, in the first column, the entries which are less than or equal to 3 are 2. There are 2 of these elements. And also in the rightmost column in the second tableau, the number of entries which is less than or equal to 3 is 1. Here's 1. So the total number of entries satisfying this condition is 3, so it is okay. And for other values of k, we can check that this condition too is also satisfied. So when there's such tableau and define B sub mu to the set of these by tableau. But in fact, in the previous definition, if we only allowed entries in these two byte tableau to be the set of positive integers from 1 to n or 1 check to n check, then our set of byte tableau is just the set of rational Young tableau for GLN introduced by Stanbridge. And Stanbridge's rational Young tableau parameterizes the basis for the finite dimensional irreducible representations of GLN. So our definition is somehow a limit of the Stanbridge's rational Young tableau. And also by definition, this set can be naturally embedded in the tensor product of these two crystals. One is highest one and the other is lowest one. So anyway, we can apply the Cauchy-Riemann operator on the right-hand side, and we can check that actually this set is invariant on Cauchy-Riemann operators. So we can prove that it forms a GL positive crystal, and also it is connected, even though it doesn't have a highest weight or lowest weight element. And also this set of byte tableau is isomorphic to the extremal weight crystal corresponding to the integral weight lambda, whose phi group orbit is mu and u. So we have a combinatorial realization, and my next question is, what happens if we take tensor product of two extremal weight crystals? Of course, when nu, the second component in nu and tau are empty, if they are empty, then this is just the tensor product of two highest weight crystals. And in this case, the tensor product of these two highest weight crystals is a disjoint union of some other highest weight crystals, and the multiplicity of each connected component is exactly the same as the number of the literal Richardson tableau, or the multiplicity is given by literal Richardson coefficient. But so now I want to talk about what happens if we take the tensor product two extremal weight crystals. So for this, let me introduce an insertion algorithm for this set of byte tableau. Of course, I mentioned that my realization is limit of Stanbridge's rational Young tableau, and also there is an insertion algorithm for the rational Young tableau for GLN. So we have to modify it to the limit case. So, but I'm not going to define I'm not going to give a full description of the insertion algorithm, but instead let me just give a few examples. So let us consider the insertion of this letter to this byte tableau in extremal weight crystals. And actually this insertion consists of two steps. And as a first step, we take the second tableau. And now we read the entries in this tableau column by column from left to right. And then we stop when you first meet the entry, here in this case, when you see the for check. And then we take a subsequence in this first column, which is starting from for check and increasing by 1. Then we take the maximal subsequence in red sequence here, and then replace it by adding 1 in each element. And also we replace our 4 by 6, which is the smallest element in this red sequence. And now, as a next step, we take the first tableau and apply the usual column insertion and take this new tableau here. So we define the insertion of this letter to this byte tableau to be the pair of tableau we have obtained in these two steps.
Why don't you have 7 check your output from the first step of your algorithm? I missed that.
Here?
No, in the right tableau.
Yeah,
Because it wasn't.
You,
You're supposed to take the sequence. Going to have to be consecutive.
okay. Second.
Yeah. Thank you. So now let me consider the case of insertion of check letters into the bitablet in extremal weight crystal. And then also this insertion consists of 2 steps. So we take the second component. And now we consider the reverse row insertion of this letter to this tableau from the bottom row. So we obtain this tableau. So the 3 check is bumped out, bumped out, bumped out, bumped out. But if we consider this pair of these 2 tableaux, then it is not an element of an extremal weight crystal, because if we consider 4, then the entries in the first column less than or equal to 4, and the number of entries in the first column here which are greater than or equal to 4 check are 2 and 3. So it is 5. So it does not satisfy the condition I mentioned in the previous slide. So we have to modify it. So still we apply the row insertion, but we stop the row insertion procedure when the condition 2 in the definition are not satisfied. So we have to stop when 4 check was bumped out in the 3rd column. Oh, yes, right here. And then we take the first component, then there exists still 4 in the first column here, and we remove it, but it's not a Young tableau, so we play jitter tucking to obtain new tableau here. And we define the insertion of this letter to this bitablet to be the pair of tableau we obtained in the previous steps. And furthermore, this insertion algorithm is well compatible with the crystal structure. This means that actually the insertion of A into the pair of S and T is crystal equivalent to the tensor product of S and T tensored by A. The crystal equivalence means that the both sides, these elements can be viewed as a crystal element. And the equivalence means that there exists an isomorphism of crystals from the connected component of the left one and to the connected component of the right one. And also the isomorphism sends this element to the right one. And also when we insert the check letters to the bitableau, still we have a crystal equivalence property. So these 2 elements are crystal equivalent. So summarizing, we have the following decomposition of a crystal. So if we consider the extremal weight crystal B sub mu nu tensored by the crystal of natural representation, then it is a disjoint union of still extremal weight crystals B sub lambda nu. Here the second component is fixed, but the first component is exactly increased by 1. Of course, from the insertion algorithm, that we have a bijection from the left-hand side to the right-hand side. But from this crystal equivalence, we can check that the bijection is actually an isomorphism of a crystal, which means that the bijection commutes with the Kashwara operators. And similarly, we have when we take tensor product by the dual of the natural representation, then we have the following decomposition. So first one is here the first component is fixed, but the second one is increased by 1. But in this part, the second component is fixed and the first component is decreased by 1. And we can easily generalize the insertion algorithm to obtain the theory rule for extremal weight crystal. This means that if we consider the tensor product of B sub mu nu and the crystal of which corresponds to the partition K, this is the crystal of the K symmetric power of the natural representation, then it is isomorphic to the disjoint union of extremal weight crystal here, And the second factor is fixed, but the first one is increased by just horizontal K street. And similarly, if we take tensor products by the dual of the K symmetric power, then we have similar description, but in this case, both components are changed. So the first one is decreased by horizontal P street, and the second factor increased by horizontal Q street, and the P, Q are where the sum of P and Q is the given positive integer K. And still, we can generalize the insertion algorithm to the case of inserting a bitabler to the bitabler case. So actually, we can check that the tensor product of two extremal weight crystals is a finite disjoint union of still extremal weight crystals. And also the finiteness is also important property. So we have only finitely many components here. And from the insertion algorithm, we have the following interesting fact, that actually the extremal weight crystal is isomorphic to the tensor product of lowest weight crystal and the highest weight one. I have to remark that the tensor product in when you consider the highest weight crystals, the tensor product is commutative. So the A tensor B is isomorphic to B tensor A. But if we consider both highest weight and lowest weight crystals, the tensor product is no more commutative, so we have to be careful. So now I want to talk about the multiplicity of each connected component in tensor product of two extremal weight crystals. So for this, let C be the category of dual positive crystals where each object is just finite disjoint union of the extremal weight crystals. And we have just checked that the tensor product of these two crystals are still finite disjoint union. So naturally it is closed on the tensor product. And let K be the Q space, which is spanned by the isomorphism classes of each element in this category C, and subject to the relation so that the sum of two isomorphism classes is equal to the class of the disjoint union of these two crystals. So it is a Q vector space with the basis is the set of extremal weight isomorphism class of extremal weight crystals. And also I have said, I told that this category is closed on the tensor product, so we can naturally induce the multiplication in this space by the tensor product crystals. So it forms a Q algebra with a unity, and the unity is the isomorphism class of trivial crystal, and the multiplication is given by the tensor product of crystals. And I have some remarks. So if lambda is the algebra of symmetric functions in an infinite number of variables, and also if we take K plus to be the subspace of K, which is spanned by the isomorphism classes of highest weight crystals, then it is naturally isomorphic to the algebra of symmetric functions. The class of highest weight crystals corresponds to the Schur functions with the same partition mu. And of course, we can take the subspace, say, K minus, which is spanned by the class of lowest weight crystals, and and also that is isomorphic to the algebra of symmetric functions. So in this space K, we have a two copy of algebra of symmetric functions, but as an algebra, K is not just the tensor product of two algebra of symmetric functions, because K is Thank you. Yeah, I want to talk about these things later. Yeah. But K is not commutative, so we have to further study about the algebra structure on this Grothendieck ring. So for this, let me just recall some basic properties on the ring of symmetric functions. So on lambda, there is a whole linear product where the set of short functions form an orthonormal basis. And let f for a given symmetric function f, let us denote by just f the operator induced by left multiplication. And f perp is the adjoint of f with respect to whole linear product. Actually, these things has already introduced in Professor Okada's talk. And now I want to consider the algebra A, which is a sub-algebra in the linear endomorphism algebra of lambda, which is generated by f and f perp for all symmetric functions f. And also we know that the lambda is isomorphic, or can be viewed as a free commutative algebra whose with variables the case symmetric, power symmetric functions pk of x. And also pk perp is just the k times the partial derivative with respect to this pk variable. So this algebra A is nothing but the ring of differential operators with polynomial coefficients, and also called the Weyl algebra, and in this case it is Weyl algebra of infinite rank. And actually we can show that as a K algebra, K is isomorphic to A. And the isomorphism is given by sending this extremal weight class to the composition of two operators, SNU and SMU perp. So this mu nu goes to differential operators, and the tensor product here or multiplication here corresponds to the composition of two differential operators in this Weyl algebra here. So let me just give a sketch of proof. So let us consider this generating function introduced by Professor Okada. And the coefficients are the operator hk and hk perp, which are the joint of these coefficients. And hk is a complete homogeneous symmetric function. And we have a commutation relations. And in terms of coefficients, we have the following commutation relations for these proper operators and usual multiplication operators. And also, we have obtained from the Peary rules that the following decomposition of the tensor product of two extremal weight crystals. So actually, we can see that the BS perp corresponds to these operators, and B sub MTR corresponds to these operators. So if we consider the isomorphism classes of this decomposition in K, then exactly coincides with the commutation relation of these two generating functions. And also, these relations can be viewed as defining relations for the Weyl algebra A. So we have a natural linear map, natural homomorphism of algebras from A to K, sending HR to this one and HS pop to this one, and hence the operator SNU and SMU perp goes to the extremal weight crystal. And comparing the basis of two sides, we can show that actually this homomorphism is an isomorphism. So what is the decomposition number or multiplicity of each connected component? So let us simply note capital C to be the multiplicity of this component in this tensor product. And from the previous isomorphism, this corresponds to this differential operator. And also they form a basis of A. And from the isomorphism, that the multiplicity of our each connected component is nothing but the structure constants of A with respect to these operator bases. And actually, the decomposition number here is given by the sum of the product of four usual literary Richardson coefficients, like this form. So at least to me, it's a very nice form. So let me give a sketch of the proof here too. But if we just before considering proof, let us take a look at this equation. So if mu and sigma are empty, then the product of these, or composition of these two operators, still satisfy the usual-literary-Richardson rule. And also, if nu and tau are empty, then these two proper operators still satisfy the usual-literary-Richardson rule. So to determine this decomposition number, we have only to know about the computation relations of S mu perp and S tau when nu and sigma are empty. Then we can apply the usual literary-Richardson rule after the computation relations. Then we obtain these decomposition numbers. So what I mean is that, so first we consider the generating function h of x, which is the product of h of x1 and x2 and so on, and similarly as h pop of y. And from the computation relations, we still have the following relation: product identity. And also by applying usual quotient identity, the generating function h of x can be expanded into the sum of these forms, the s lambda times s lambda of x with the operator coefficients, and also h pop of y have a similar expansion. And then if we put this expression to the above identities and comparing the coefficients of the double symmetric functions in both sides, then it's just an exercise, but still we have a computation relations of this form. And then if we use these computation relations to this identity and apply the usual literary-Richardson rule 2 times more, then we obtain these decomposition numbers. So 10 minutes. So, okay. So finally, let me, oh. I want to talk about some application of the characterization of the Grothendieck ring or the decomposition number. So I want to define an analog of characters for extremal weight crystals. Why I have to talk about analog for characters? So unlike the case of highest weight crystals, we cannot define the characters of extremal weight crystals in general, because usually the weight space of extremal weight crystals have infinite dimension, so we cannot define the character of an extremal weight crystals. But what I still want to define an analog of characters. So I want to define some kind of functions in non-commutative variables whose product still explain the literary-Richardson rule we have obtained in the previous slide. So let me just remark some facts first. So we know that the algebra A, the via algebra, acts on the ring of symmetric functions as differential operators. And from our identification or isomorphism, this action has a very natural representation theoretical meaning. So this means that if we identify the lambda with the space K plus the class spanned by the highest weight crystals, then the operator multiplication induced from multiplication SNU is equal to the tensor product of 2 crystals and can take its isomorphism class. But it's not so interesting. But in the second, but if we consider the pop operator or the adjoint operator, then it's very interesting. So applying SNU perp to the show function SMU corresponds to the composite of 2 functors in our category C. So this means that we first consider the tensor product of highest weight crystal and lowest weight crystals, and then we project it to the subcategory of highest weight crystals. That exactly explains the adjoint operators in this identification. Anyway, assuming these observations, let me let me introduce Schur operators. So for simplicity, let us denote by bracket lambda be the class of highest weight crystals, be lambda here. And now for a given GL positive crystal B and for any element small b, let me define the operators. Say U sub B, which acts on K plus, and it is defined by in the following manner. So U sub B of mu is equal to the bracket lambda if the highest weight corresponding to mu tensored by our element B is crystal equivalent to the highest weight vector corresponding to lambda. If this is so, then we define U sub B of mu to be lambda, and otherwise it is 0. And then our operators SNU and SNU perp can be given as a sum of U operators, where each of U operators are parameterized by the semi-standard tableau in highest weight crystal corresponding to mu, and perp case the operators are parameterized by here still the crystal element in this lowest weight crystal. And I want to further refine this operator U sub S and U sub T. So if we recall the tensor product rule of crystals, then in general, if we consider some finite elements in this crystal B sub 1 from B sub R, then the associate U operator corresponding to the tensor product of these elements is just nothing but the composite of each U operators corresponding to B sub I. So, and also let me introduce one more simple operators. So when it comes to the natural crystal of natural representation and its element A, say positive integer, then we can define U sub A operators. And also U sub A check operators. And then U sub A, when applied to mu, is nothing but it's lambda if lambda is obtained by adding a dot in the eighth row of U, and otherwise it's 0. And similarly, U sub A check mu is lambda if lambda is obtained by removing a dot in the eighth row of U, and 0 otherwise. But as you might know, this is not the new operators. Actually, it was introduced by Bonin and called the Schur operators. And so, if we combine this observation and the observation, also in the previous slide, that for each semi-standard tableau S and T, actually the U operator here corresponds to the U operator coming from the column word of S, and also U sub T is equal to the U operator corresponding to the column word of T. So they are just the monomials in the form of Schur operators. So the SNU operator is still the Schur functions, but in this case it is using in non-commutative variables U sub I, and SNU perp is the Schur functions in non-commutative variables. And so our isomorphism from the Grothendieck ring K to the algebra A, actually, if we view it as SNU and SNU perp as the functions in non-commutative variables Schur operators, then so this isomorphism can be viewed as a non-commutative analog of the classical character map from the Grothendieck ring of highest weight crystals to the ring of symmetry functions. And also, I would like to remark that this proposition, so the operator here, and SNU and SNU perp can be viewed as a non-commutative Schur functions, was already proved by Fleming by a purely combinatorial way. So in my case, I gave another proof using another simple proof using the theory of crystals. So finally, let me give some remark. So today I have talked about the A plus infinity case, but there are still other cases of infinite rank affine types. So what about A infinite case. So the linking diagram of this Lie algebra is the two-sided infinity of the finite rank case. Then we have a very similar results, which can be done in a separate work. So we consider in this category, in this case, the category of extremal crystals with the non-negative level. So there's some technical condition, and we can also prove that this category forms a monoidal category on the tensor product. So we can form the Grothendieck degree. And so, as in the case of A plus infinity, so we may expect that the Grothendieck ring for this Lie algebra can also isomorphic to some ring of a differential operator, some certain ring. But yes, so it was true. So in this case, we consider the formal power series is an infinite number of variables, Zk, and here k is not positive integers, it's a whole integer, and we consider the formal power series with bounded degree. And then we consider the derivations gamma I, some infinite family of derivations gamma I, and they are all commutative. And we take an OR extension of this formal power series ring with respect to the derivations. Then the Grothendieck ring of this type is isomorphic to the opposite. And still we have a combinatorial realization, and also we still have a little recharging rule for this type, very explicitly. And also, using our combinatorial model, we can also give a combinatorial realization of some homogeneous part of the Lucix modified quantum group. Yes, that's all for my talk, and you have already seen this many times.
Thanks
Thank
for
you
being
again.
here.